Welcome back, everyone, to today's Explainer, where we're going to break down exactly how virtual private networks secure your data across the incredibly chaotic public internet. Today, we're zeroing in on the architecture of IPsec and its highly trusted partner, IKE.
Picture this for a second. How do you securely pass a secret across a completely packed, noisy room? Right? It's tough. Anyone could be listening, you really don't know who to trust, and you certainly can't just shout your private password out loud for everyone to hear. Well, that is exactly the problem the open, unencrypted internet presents when you're working remotely or accessing your bank. Today, we'll see exactly how IPsec and IKE team up to solve it.
Here is our roadmap for today. We'll be covering securing the network layer, how IPsec protects data, the complexity of IPsec, introducing Internet Key Exchange, IKE phases and versions, and finally, the complete VPN blueprint.
Let's jump right into part 1, securing the network layer. You know, at the network boundary, you'll constantly hear IPsec compared to SSL or TLS VPNs, and they are very different beasts. While SSL VPNs protect specific applications and operate up at the transport or application layer, usually granting access right through your web browser, IPsec is entirely different. Think of IPsec as a heavy-duty armored truck operating directly at the network layer. Because it sits down at layer 3, it inherently secures all transit packets, making it the undisputed gold standard for robust site-to-site tunnels.
Which brings us to part 2, how IPsec actually protects that data.
Think of the Security Policy Database, or SPD for short, as this highly intelligent bouncer at the door, deciding exactly which IP packets need to be processed and protected. Once those rules are matched, IPsec relies on what's called a Security Association, or SA. You can think of the SA as a highly specific, unique contract for that exact connection. It keeps track of the security parameters index, the destination IP, and the protocols for both inbound and outbound traffic. Now, when IPsec goes to work on your data, it basically has two main tools. It can use ESP, the encapsulating security payload, or AH, the authentication header. ESP is your true vault. It absolutely encrypts the payload so literally no one can read it, while also ensuring the data's integrity. AH, on the other hand, is more like a tamper-evident seal. It guarantees the data hasn't been messed with and verifies the source. But, and this is a big but, it leaves the actual payload completely unencrypted. So why is ESP far more common today? Simply because keeping your personal data private through encryption is just as critical as verifying its integrity.
Okay, so how does this armored vault actually travel across the web? IPsec uses one of two modes. It can use tunnel mode to wrap the entire original IP packet, header and all, inside a brand new packet. This is your standard gateway-to-gateway secrecy over the open internet. Or it can use transport mode. Transport mode secures only the payload and leaves the original IP header intact, which is absolutely ideal for lighter end-to-end host communications.
Moving on to part 3, the complexity of IPsec.
Look, we have to be honest here. The tough reality is that IPsec is notorious for being incredibly complex. Honestly, kind of over-engineered. The protocol is packed with all these extra features that historically made interoperability a massive headache for network admins. You'd have devices from different vendors that just flat-out struggled to talk to each other, which, ironically, completely defeats the purpose of having an open standard in the first place.
And that complexity really hurt early deployments. Back in its infancy, IPsec relied entirely on manual keying. I mean, imagine network administrators literally having to statically configure symmetric encryption and authentication keys into both endpoints by hand. Total nightmare, right? It lacked any standardized mechanism for automated key rotation and couldn't easily validate distant peers. Ultimately, this created severe operational bottlenecks and, frankly, massive security vulnerabilities.
Thankfully, we got a fix for that. Part 4, introducing Internet Key Exchange.
Enter IKE, the Internet Key Exchange, or if you're in a Cisco environment, you might know it as ISAKMP. To solve those scaling issues, network engineers did something really smart. They completely decoupled key management from the data engine itself. So IKE acts as the control plane. It's the secure handshake that authenticates the peers, dynamically negotiates those cryptographic keys, and safely decides who actually gets to drive the armored truck.
And the real mathematical magic behind how IKE does this over a public channel? That would be the Diffie-Hellman algorithm. Diffie-Hellman allows both sides to independently generate the exact same shared symmetric key, using a mix of public and private components.
The sheer brilliance here is that since the keys are derived independently by both peers, the actual symmetric key is never, ever sent across the open internet. It stays totally safe from anyone trying to eavesdrop.
All right, part 5, IKE Phases and Versions.
IKE basically splits its job into 2 strict phases. Phase 1 is all about establishing trust. It builds a secure, authenticated management channel between the 2 peers. Once that safe space is created, Phase 2 takes action. Often called quick mode, Phase 2 uses that newly secured channel to negotiate the actual IPsec security associations that are going to encrypt your everyday data plane traffic.
Now, over time, the industry realized that IKEv1 was just way too rigid with its complex main and aggressive modes. So they introduced IKEv2 to drastically simplify those exchanges, meaning it requires far fewer messages to establish a connection. IKEv2 is also a huge step forward because it features built-in NAT traversal for better reliability, and it smartly separates out the rekeying and reauthentication processes.
Instead of those clunky version 1 modes, IKEv2 operates over UDP part 500 and boils things down to just 4 core message exchanges. You start with IKE_SA init to negotiate algorithms and establish that Diffie-Hellman secret. Then IKE auth steps in to authenticate identities and create the very first IPsec SA. If you need additional tunnels later, you just use create child SA. And finally, informational handles all the control plane maintenance and error messages. It's just an incredibly clean, efficient process.
Let's put it all together. Part 6, the complete VPN blueprint.
If you take away just one thing from this explainer, let it be the sheer brilliance of this division of labor. IKE is your control plane, the keymaster. It safely produces the keys and authenticates the users. And then once it finishes negotiating that trust, it just hands those parameters right off to IPsec. IPsec is your data plane, the vault. It takes over, utilizing protocols like ESP to actually encrypt and fiercely protect the bulk transit of your packets.
But, as we know, network security never actually sleeps. With quantum computing emerging on the horizon, it begs the question, will your VPN's Diffie-Hellman mathematical keys remain secure, or is the era of quantum-safe IPsec tunnels already knocking at our door? That is absolutely the next frontier of network security to ponder. Thank you so much for joining this explainer, and always keep questioning how your data travels.